Hi, I'm Dr. Chen, and I'm making a quick tutorial on how to do some preliminary steps here prior to fitting a multi-level model. Specifically, we're going to talk about how to identify a suitable functional form, and we're going to do that by creating some empirical growth plots based on OLS regressions. And then also going to do the same thing, but do it for subgroups, and that's for us to examine if our group level predictors are good enough predictors for us to predict the estimated individuals' true initial status as well as their rate of change. So a couple of things before we go into this. This presentation is adapted from Singer and Willett's 2003 textbook and web page. So I would encourage you to go to that resource if you want the original PowerPoint presentations. It's really useful. And also, I took the R syntax for this tutorial from the UCLA Statistical Consulting group page. As you can see, they have a number of different types of syntax for SAS, data, R, SPSS. So really cool, really gives you a lot of options in terms of how to recreate some of the examples here. Specifically for this tutorial, we are going to work on two things. We're going to try to create some growth plots to figure out if it's a reasonable assumption for us to assume linearity between time and our outcome of interest. And then we're going to create some subgroup plots to figure out if our group level predictors are doing any good, visually at least, in terms of being predictive of the individual's estimated initial status and their rate of change across time. So the data set is based on the data set that was collected by Karan, Tice, and Chasen. They collected 3 waves of longitudinal data on 82 adolescents. Age 14, teenagers complete 4 instruments that is their 8-point scale, ranging from 0 through 7, 0 meaning not at all, 7 through every day, and they describe the frequency which they drink. They drank any type of alcoholic beverage. So this is the outcome of interest over here, and so it's just really nice for us to know what exactly are we measuring in terms of the nature of the construct or the index that we're trying to track here. There are 2 predictors that are of interest in this particular tutorial. And also in future examples, which is COA and peer. COA is basically a dichotomous variable that indicates whether the adolescent is a child of an alcoholic parent or not. So 0 being not a child of an alcoholic parent, and 1 being, yes, a child of an alcoholic parent. And so we want to see if that is going to be a significant predictor of the individual's estimated true initial status. So the alcohol use at time point 1, and as well as the rate of change, to what extent is their alcohol use changing across time. And peer is the other predictor, which is basically a measure of their peers' alcohol use at the beginning of the experiment. Now, this is going to be a time invariant predictor. I'll have future videos next time that talks about how to deal with time varying predictors. But for this one, it is a time invariant predictor. We're only going to look at their peers' alcohol use at time point 1 and see if that is going to be a predictor of the individual's estimated true initial status, how much alcohol they're using at age 14, as well as whether or not that changes across time. And the specific measurement here is they're rating their friends' alcohol consumption on a 6-point scale, 0 meaning none, 5 to all, in regards to the proportion of their friends who drink alcohol either occasionally or regularly. So the research question here is basically, do the trajectories of adolescent alcohol use differ by parental alcoholism or peer alcohol use, specifically at time point 1? So one of the first things that we want to sort of figure out is if it's reasonable for us to assume a linear relationship between time and alcohol use, because if a straight line between between time and alcohol use is not a good summary of how your alcohol use is changing over time, then we may want to use other types of functions to connect these two variables. And so I'll have another video that talks about how we should examine assumptions of normality, homoscedasticity, and linearity. But for this one specifically, we're talking about checking out the assumption of linearity between time and our outcome of interest. So this is actually figure 4.1 in page 77. And we're randomly selecting about 8 individuals, person in ID 4, person in ID 14, so on and so forth. I'm going to fit OLS regression lines over here to see if if it's reasonable for us to assume a linear relationship between time and age. A quick note over here. So what the authors tell us in chapter 3 is that they had to transform alcohol use and peer by computing the square root of alcohol use and peer in order for us to be able to assume linearity between age and time and age and peer. And so what we're looking at technically is basically the result of alcohol use after they transform it by a square root. And so again, we'll talk about transformations in another video, but just to give you a sense of the nature of the data here. So if we're just looking at this figure 4.1, it does seem like, maybe it might make sense, because we can see over here for for individuals with ID 23, 32, 56, and 65, a straight line does seem to do a fairly good job of capturing how alcohol use changes across time. Whereas for individuals with ID 4, 14, 41, and 82, so like this one, for example, this straight line obviously is not doing a very good job of describing how alcohol use changes across time, but it does seem to change across time. It'd be really nice if you had more data points, and that's the reason why people who do longitudinal data analysis usually recommend having at least 3 or more time points for us to really know if there is a trend. So we're just going to go ahead and say, just based on this visual inspection, some people would use the fancy word ocular inspection to figure out if it's reasonable for us to assume a linear relationship between time and our variable of interest. And so in this model over here, by the way, note that we're talking about a multi-level model change. So when you talk about multi-level model change, that should tell you that there are different levels to this model of change that we do. So specifically, we're only going to deal with a 2-level model change. This particular formula over here is referring to the level 1 submodel of change. We're going to talk about a level 2 submodel change in just a little bit, but let's just talk about the level 1 submodel change and try to unpack what exactly is this about. So we're basically saying that each individual's alcohol use at a specific time point, so that's subscript I and J, equals to the estimated individual's true initial status. So that's the alcohol use, individual's alcohol use at time point 1, plus the estimated individual's true rate of change, so that's represented by pi subscript 1i per unit of time, so that represents the slope. And epsilon over here represents the portion of the outcome that is unexplained on occasion J. So basically the proportion of the individual's outcome that is unpredicted on occasion J. So the extent to which this level 1 submodel is not able to capture the variability. So again, remember, this is the level 1 submodel, because when you talk about the level 2 submodel, our fixed effects, which is basically the intercept and slope, are going to be the outcomes of group level predictors of change. And so just kind of hold on to that thought, because we'll come back again to that. For right now, I just want to quickly show you how to recreate this set of graphs over here for us to be able to check out functional form. And so this is what is shown in the textbook. This is what we should recreate. We're going to go ahead and go into RStudio for us to recreate that. So once you have the R Markdown file and your data set in the same folder, you can just go ahead and import the person level data set. We call this, oops, what just happened? Okay. I'll call one read a table. That's the name of the data set. And it's separated by commas in terms of the data, and the header equals true, which means we have headers in the data set. Get that right. Alcohol 1 equals to read.table. Why is it showing me an X? Oh, I forgot equal sign. Okay, I might need to set the working directory over here because something weird happened with my computer earlier. Okay, so there you go. So we've actually then just cleared that. So we can start with the clean slate. So we have the data set alcohol 1 with 246 observations and 9 variables. Let's use the summary function. You get some descriptive statistics over here. So we'll see, for example, that age is 14 to 16. We also have a centered age variable over here because we want the intercept in our regressions to represent basically the alcohol use at age of 0. So there are reasons as to why you might center our variables. We'll talk about that in another video. And this is how they set person, like example. This is COA, this is gender, this is alcohol use, this is peer, and these are the centered variables for peer, COA, as well as for age. If you want to pull the names, you can pull names using names. Okay. So let's create those plots. First of all, upload the lattice library. If you don't have this package installed, you may want to type in install other packages in order to find the package. So that's simply install that package. Like that. It'll search the right cran mirror for you to download it. And let's go ahead and type out the function here. So XY plot. I'll use regress on age. Do this at ID. I'll call 1. I'll call 1. Specifically, we want 4, 14, 23, 32, 41, 56, 65, 82. Got that right. Panel. Y. Line there as well. Upper and lower limits for the y-axis, -1. Okay. Get that right. Fine function. Okay, let's see. Oh. Okay. There you go. Okay, so now we've got the empirical growth plots for people with ID 4, 14, 23, 32, so on and so forth. So this should look pretty similar to these figures over here. All right, ID 4, 14, so on and so forth. Okay, so now we're going to move on to making similar plots, but we're going to do it for subgroups. Specifically, we're going to do it for those with whose kids, whose parents are non-alcoholics, and kids whose parents are alcoholics. That's represented by this graph here and this graph here. And we're also going to create another subgroup plot for those with low peer and high peer. And the reason why we do this is so that we can do a very similar type of visual inspection here. And basically, we want to know if our group level predictors, COA and peer, actually doing any good in terms of being able to predict the initial status of individuals as well as the rate of change. So we can see over here, for example, that kids whose parents are alcoholics, that's represented by COA equals to 1, they do seem to have a high intercept compared to parents whose kids who have low, whose parents are non-alcoholics. That means that kids whose parents are alcoholics, they tend to drink more alcohol when they're age 14. So that may make sense. And then for peer, we're actually going to split, because peer is a continuous variable. We're going to split this into half. So those whose friends are not who has a low proportion of friends who drink regularly, and kids who have a high proportion of friends who drink regularly. And we see very interestingly, so it really does seem that peer is a very powerful predictor. Kids who has a lot of friends that drink regularly, their intercepts are higher. That means they drink a lot more alcohol at age 14, but their slopes actually are not as steep as compared to this one. So all this to say, it does seem as though like these group level predictors, parents as well as peer influence, they do seem to be good predictors of the individual's true estimated intercept and rate of change. So I want to show you an extension of what we talked about before. So before, you may recall this particular formula right here. The individual's alcohol use is a function of the estimated individual's true initial status in regards to alcohol. So this is the intercept plus the rate of change, the estimated true rate of change for each person, multiplied by time per unit of time, plus epsilon ij. So this represents the individual's outcome that is not predicted by any of these parameters at the level 1 submodel. So notice, if you remember, I said that these two fixed effects, pi 0,1 and pi 1i, are actually going to be outcomes on the level 2 predictors or the level 2 submodel. So we'll see, for example, that pi 0,1, so the individual's estimated initial status, how much alcohol they're drinking in the very beginning, is going to be a function of these parameters here, which is basically gamma 0,0, gamma 0,1 multiplied by COA, whether or not your parents are alcoholics or not, as well as zeta 01. So what do these parameters mean? Well, gamma 00 represents the estimated population's initial status, specifically for kids whose parents are non-alcoholics, for COA equals to 0. So this represents the population's average intercept for kids whose parents are non-alcoholics. Gamma 01, on the other hand, represents the effect of having parents who are alcoholics. And what does that do to the population's average initial status? And zeta 01 represents the deviations from that population initial status. Pi 1i, remember, this represents the individual's estimated true rate of change. That is going to be a function of the group's average rate of change for kids whose parents are non-alcoholics. And it's also going to be a function of the, how having parents who are alcoholics, how that impacts the rate of change. And then zeta 1i is the deviation from the population's average rate of change. So these are level 2 residuals, zeta 01 and zeta 1i. We assume that these residuals are normally distributed with means of zeros, with a variance, with specific variance estimates, as well as some covariance between these two variants. So this basically describes the distribution of where these estimates are coming from. Here's another way to look at it. Gamma 00, gamma 10, this represents the population average initial status and rate of change for non-COA, for kids whose parents are non-alcoholics. This one, on the other hand, represents the effect of COA, having parents who are alcoholics, on the initial status, on the population's initial status, and the rate of change. So they're all kind of connected. And the more you kind of look at this, the more you work with, longitudinal data and multi-level models, the more this will come a little bit easily to you. So I'm going to show you how to recreate these empirical growth plots for subgroups. Specifically, I think I might just do this one, representing the empirical growth plots for kids whose parents are non-alcoholics. And I'll show you how to do a similar thing with kids whose friends, who don't have a whole lot of friends, who drink a whole lot. Just for the interest of time over here. So how do we create this plot over here? Empirical growth plots for kids whose parents are non-alcoholics. Okay. So first of all, we want to alcohol.COA. We want to select participants whose COA value equals to 1. If you wanted to do a similar growth plot for kids whose parents are alcoholics, this will be 1 instead of 0. And we're going to split the data set into separate frames by ID. 280. Presenting OLS regression. This works. Let's see here. Oh, okay. I missed the 0 at the very top. That's why I wasn't able to locate that object. Okay. And then now we're going to transform that data set from list to vector and then strip off the names. And let's plot it. Do this by ID. The response is going to be this data set that we just created based on the OLS regressions. Name the axes. Set the minimum, maximum, the y-axis. This is just the width of the lines. And this just gives it the title. And there you go. This is the empirical growth plot for kids whose parents are non-alcoholics. Let's go ahead and skip to this one just for the sake of time here. You're going to create the same thing, but for kids who have low proportions of friends who do drink a lot. So that's pretty easy. First of all, we want to get the mean. So it's 1.01756. Alcohol here. One if you're equal to or less than 1.076. Okay. It's just I'm gonna copy and paste these functions here so I don't mess myself up with typos. So we're gonna call this something different. Let's call this f.lope here. And this is gonna be based on the data set that we just created, alcohol.lope here. Go. And then we are going to transform it. Just a vector, remove the names. We're going to make the plot. just create it here. That's this graph right here, which should be similar to what we have right here. And so if you wanted to create the high peer one, all you're going to do is just select the correct subpopulation. So go back up over here. And instead of saying less than or equals to 1.0756, just make it more than 1.0756. Okay. So some conceptual things here before we end our video. Just a reminder again, we've got the level 1 and level 2 submodel. So this is the level 1 submodel. And for the level 1 submodels, the parameters pi 0i and pi 1i, which is the individual's estimated true initial status and individual's estimated rate of change. Each of these things are going to be a function in this particular multi-level model, at least that we're testing. It's going to be a function of group level predictors, specifically coming from gamma 0, 0, gamma 0, 1, gamma 1, 0, and gamma 1, 1. And then we also have the respective residuals at the level 2 to capture the amount of variability of each person's individual's change trajectory from the population group average. So what happens then if we were to actually substitute these level 2 parameters into this level 1 parameters, right? Given that these parameters are simply just outcomes of the level 2 parameters. Well, we actually get something like this. Yij equals to basically these level 2 parameters and the level 2 parameters for rate of change right here. And so if you were to multiply and expand this, we actually get what we might call the composite multi-level model of change, or it's basically the same thing. As you can see over here, gamma 0, 0, this represents the population's average initial status for kids whose parents are non-alcoholics. And then we've got gamma 0, 1, which basically represents the effect of having parents who are alcoholics on the population's average initial status. And then we've got zeta 0, 1, so that represents the level 2 residual. So the individuals scatter around the estimated population average in terms of the initial status. And then we've got some of the things over here. So we got y10, so gamma 10. So this represents the population's average rate of change for kids whose parents are non-alcoholics. Gamma 11, so this represents the effect of having parents whose having parents who are alcoholics, and how does that affect the slope in terms of the population's average slope. And then this is basically zeta multiplied by time. So this formula here is basically the same as this formula here, which is basically a combination of a level 1 and level 2 residuals. So the composite specification shows how the outcome depends simultaneously on the level 1 predictor of time and the level 2 predictor of COA as well, correct? Because remember, time is actually a level 1 predictor, but COA is a level 2 predictor. And then you can also see how the outcome depends on the cross-level interaction between the level 1 predictor and level 2 predictor, which is kind of cool. And also demonstrate the complexity of the composite residual. This composite over here is a combination of level 1 of the level 1 residual epsilon ij. So each individual's scatter around their estimated true trajectory. And then we've also got the level 2 residuals over here, which represents each individual's change trajectory from the population's average change trajectory. So this is not regular OLS regression anymore. And this is what allows us to make a couple of assumptions, such as autocorrelation, the idea that our scores across time is going to be autocorrelated, and also allows for heterogeneity in terms of the residuals at level 2. This is the specification that's used by most software packages for multi-level modeling. It's also the specification that maps most easily onto the person period data set. So this is the person period data set, and this is the composite formula that we just came up with. So you can see alcohol use is indicated by this variable over here. Age minus 14 is just a centered variable of age. COA comes over here, and this is basically the multiplication of COA and age 14. I also want to bring your attention to how we use brackets to indicate the fixed effects of the multi-level model and the stochastic effects over here as represented by these second brackets. And so this is really important, especially when we talk about different types of estimations and how to interpret them. So we'll come back again to the distinction between fixed effects and stochastic effects of our models in future tutorials. So a couple of tips over here. Before you go ahead and fit your multi-level models, be sure you examine the empirical growth plots and the fitted OLS trajectory. So just like how we showed you in creating those empirical growth plots using R, go ahead and do that just to make sure that it's a safe assumption for you to assume linearity, and that your group level predictors are actually making a difference in terms of being able to predict the individual's estimated initial status and rate of change. Be sure your person period data set is correct as well. Run some simple diagnostics. Make sure that you don't have a data set that has errors in them, basically. Don't jump in by fitting a range of models with all kinds of predictors. What we should do really, and this will be covered in other videos. First 2 steps. First of all, you should fit an unconditional means model. This is a model with no predictors at level 1 or level 2. And this will help us partition the total outcome variation. And then once you do that, you add another, you add 1 level to this, which is basically add time as the only level 1 predictor with no other substantive predictors at level 2. This will basically help us evaluate the baseline amount of change. And basically what we're doing with a multi-level model change is we are sequentially building the complexities of our models and letting the results kind of help us decide and determine what types of level 1 and level 2 predictors we will want to add to our data set. So what these unconditional models tells us, the first one tells us whether there's any type of variation that is worth exploring. And if so, where the variation lies, whether that's within or between people. So within would be level 1, between would be level 2. And then how much total variation there is both within and between persons. And this will basically provide the baseline for us to evaluate how successful our subsequent model building efforts are. So that's basically it for this short tutorial. I hope that's helpful. Again, these are really helpful steps for us to kind of visualize what's the functional form, which is basically usually assuming linearity between time and our outcomes of interest, as well as we, looking at some subgroups in terms of their relationship with time as well. So like any good project, it takes a lot of preparation for us to execute them. And so it's really worth checking out your data with these procedures over here before we start, getting too deep into the weeds with multi-level modeling. So that's all I have for y'all. Take care, and I'll talk to y'all soon.